There we go.
The 24th.
Yes. If that's what it says, that's where we're at. Yeah.
I'm not good with abstract
Me neither so much. So.
names.
All right, so finish up talking about linearity stuff. This doesn't come up a whole lot, but if it does, you want to identify it and keep track of it. Again, this is the general linear model, not the general nonlinear model. So if you're seeing nonlinear patterns in your data, you very much need to go through, well, you need to at least consider sort of what we're going to do with that, right? Now, if we see something like this, this quadratic, then that's something that very clearly needs to be addressed. Things get a little bit more questionable if we start to see something that, could be nonlinear, but we could fit a line to it. Again, remember that the concern is always that if we fit a line to a nonlinear association, we're going to underestimate the strength of that association. This X and Y are almost perfectly related. They're just related in a nonlinear fashion. If we try and estimate that with a line, we're going to say that those two variables are orthogonal when they're very clearly not, right? So wanting to go through and take a look, again, we can sort of work with some transforms, dummy code that variable into sort of a type of a piecewise type of analysis, looking at sort of the association of X and Y between this range versus this range. Some nonlinear models that we can go through and specify, or again, sometimes we can just ignore, right? Again, we are very, very good at, as humans, as detecting what we think are patterns, which often aren't patterns. They're just kind of random things the way stuff turns out. Again, think about like group assignments, right? With those group assignments, sometimes I went through and kind of mapped out kind of who got paired with who, and some people got paired with the same person over half the assignments, right? That seems not random, but it very much is random and is gonna happen, right? And so sometimes when we go through and look at data, we can see things like this where we're like, oh boy, yeah, that looks like a nonlinear pattern. Maybe it is, or maybe that's just something that came up in those data. It's hard to know. Where we would always fall back on is theory. What do we understand about it? Is there some reason for me to think that X and Y hold some sort of nonlinear relation? Because these might be the only data I have. I can't sort of grab another set and another set and another set to see if this keeps turning up in replications. I might just be stuck with this set. So what I need to go through is try and make a reasoned decision to say, is there some theoretical conceptual reason why I would expect this to sort of not X and Y not be super related until we get to on the low end of X, and then once we hit a certain point for that to kind of fall off. Maybe there is, maybe there isn't, and who knows if my sort of thoughts are correct, but this is going to start to help inform you. Is this something that we need to do to track the actual population association between X and Y, or is this just kind of something that's an oddity that's come up in this set that we'll never see again if we were to replicate, okay? And I don't know, there's no test for that. You just have to kind of, it's a thought experiment, right? So your job is to try and have at least some sort of reasoned explanation for what you've done, to be able to say, if someone will say, hey, why'd you do this? Be like, hey, these were the things I thought about, pros and cons. This is the decision I took. Okay? All right. So next thing we're going to get into is our variance assumptions. And again, remembering that our generalized linear model, like our means-based analyses, everything that we did last semester, just a special case of our GLM. So we talk about these variance assumptions a little bit differently, but in actual fact, they're the exact same thing. They're not sort of mathematically different. They just look a little bit different on how we talk about them with group versus ungroup data. So remember from last semester, we talked about our homogeneity of variance assumption, okay? Again, what we're saying here is that for our different groups, we're assuming that variability is the same across all of our groups. So if I go through and I've got condition 1, right? And here's my population distribution for condition 1. And then I've got condition 2. And we'll say that this is a study games running, and so it's a hypothetical population. Like the people these run are the only people who've ever experienced this. But if we were to do this to everybody, we would expect a distribution of scores. And then for condition 2, got this. We're expecting a shift in the mean difference, right? So that one is scoring high, one group is going to be scoring higher than the other, but we're saying that the spread of those two scores is going to be equal, equivalent across those groups, right? And then if we get into ANOVA models, we've got multiple groups, right? This is our homogeneity of variance. Remember this? Okay. So when we get into our continuous models, we've got the same thing, except we call it something different and it looks a little bit different. We've got an assumption of homoscedasticity, okay? That's a fun word to say. Homoscedasticity is just saying variability in scores for a continuous variable x is the same across all values of y, okay? Or excuse me, variability in scores for continuous variable y, same for all across all values of x, okay? So this is kind of getting into, remember when we were back in correlation talking about marginal distributions and conditional distributions. Marginal distribution is just distribution of all the scores in my set. Conditional distribution is saying for every value of y, x has a normal distribution. For every value of x, y has a normal distribution, right? Talking about that in the bivariate normality assumptions. Same thing here, what we're saying is that for every value of x, y has an equal distribution and the same variability for all values of x, okay? So basically what it's doing is we're taking the same homogeneity of variance assumption, and instead of having 2 groups or 3 groups or 4 groups, we have infinite number of groups. Any value of x, any value that x can take on, we're saying that if we just looked at that value of x, all corresponding y's would have the same distribution. And if we plot that out, we get something that looks kind of like this, okay? We get this kind of sort of oval shaped thing. So if I go through for any value of x here, and I go through, the spread of scores is about the same, okay? Now obviously we kind of got this nice little sort of kind of tapered thing. So like technically it's sort of maybe bigger in the middle than here. But like the idea is that no matter what value of the predictor we're looking at, the distribution of y's is all the same, okay? And so again, basically, we're just taking instead of a categorical x where we got 2, 3, 4 groups, we're saying we have infinite groups. For any possible value that x could take on, this holds, okay? And if we plot it, this is what this looks like, okay? People seeing sort of understanding of what this homogeneity variant or this homoscedasticity assumption is talking about. And then if we violate that, we might get something that a plot that looks something like this, right? Here at low values of x, variability in y is quite small. Everything's pretty consistent. But as we grow, as those x get larger and larger and larger, now all of a sudden y becomes increasingly more variable, okay? So again, going back to the ANOVA example, as our conditions get larger and larger and larger, variability gets higher and higher and higher. That's kind of what this is looking at here. Okay. Now, a couple different things that can start to produce these types of plots. Oftentimes our heteroscedasticity, so homoscedasticity is our assumption. Heteroscedasticity means that things change, okay? And so if we see heteroscedastic data, what we're saying, what often we'll see, and we'll see this in some examples, this is sometimes due to violations in univariate normality, okay? So if I've got 2 variables and one's super skewed, a lot of times we'll see something that looks like this, okay? And so example here, the association between income and age. If I just look at, say, the working public, right? What's the distribution of age look like? Pretty normal, right? I guess maybe sort of something. You got some older workers, younger workers, most people sort of looks pretty okay. What about the distribution of income? What does that look like? Is that normal? No, what does that probably look like, Mandy?
It'll probably look like scattered.
Yeah. If we're thinking about distributions, what does that maybe look like, Jalen? What's that?
I don't know, is it just like you don't be making money or you make a lot of money?
Yeah. And so if we were to plot that, what would that look like? How would we describe that distribution?
Linear
Yeah.
way, positive.
A positive skew, right? So we've probably got people kind of stacked up here, sort of making sort of kind of the median value, but then we've got people making increasingly high amounts of money. Now, if I go through and I plot age and income, what I might get is something like this. Someone tell me why I might see a plot like this if I'm plotting age on the x-axis and income on the y. Yeah.
Because you start getting more variability in income as
Yeah.
age increases.
Yeah. If we're all talking about 18, 19, 20-year-olds, probably down here to the low end of the stuff, like people aren't making. We're generally not seeing young adults outside of athletics and YouTube influencers, I guess, sort of making 6, 7 figures, right? Everybody's kind of making minimum wage, just kind of putting together sort of money to do sort of whatever you're doing, right? Then we start to get sort of older and older and older, right? People start to get in professional positions, more education, things along those lines, advancing in careers. And now all of a sudden you still have people who unfortunately are not making a lot of money and sort of still down here, but then you've got also people making quite large amounts of money or sort of moderate amounts of money, just more variability here, right? So if we go through and we plot this two continuous variables, one that is relatively normally distributed and one that is relatively skewed, what we start to see as people age, variability in income starts to increase. Now, what might you do to normalize that? What's a third variable that you might throw in there that would maybe fix some of this stuff?
Education?
Yeah, education. If I go through in this and I control for education, after I pull variability due to education, that probably starts to look more like that. Not 100%, and particularly for something like income where there is no real upper limit, you're going to have weird extreme values and things along those lines. But again, this is what we'll see when we get into some residual stuff, is we can see heteroscedasticity in residuals due to an omitted variable, right? If I'm just looking at this, it looks real bad. If I throw income into the mix, fixes it, because we've got that factor that's accounting for variability as people get older, right? So again, lots of things to think about here. Other thing that we can see is variability in measurement precision can start to contribute to heteroscedasticity, okay? So think about assessment of intelligence at the extreme ends of the scale. For someone taking Tara's class right now, what happens for our IQ tests, achievement tests, when we start to get very, very high values, very, very low values? What happens to the reliability of those scores? They're less reliable, right? And so if we're just looking at people sort of right there in the center of the distribution, things are looking pretty good. If we go out and we get towards the end of the distribution, things start to jump around a whole lot more. And so what we can start to see is if we're looking at, let's say, folks with perhaps like intellectual disabilities or something along those lines are looking at the lower end, what we might see is things are really variable at the low end. And then as we get sort of closer towards sort of that middle score, things kind of go down, or the same way if we flipped it around, looking at people on the high ends, right? So wanting to think about measurement, variability, and precision and how that can start to impact things, okay? So again, anytime we go through and see this type of pattern, identifying it as a thing is good, but then the big test is sort of think about like, why are my data doing this? What's happening? Because a lot of times that can sort of tell us, oh, there's something wrong with the measurement tool. I've forgotten something in this model that needs to be in there, those types of things, okay? Yeah.
On that last slide, like the little caption on like the lower plot said that the skewness was on X2. What does that mean? Like,
so this is if we're like looking at age and income.
Mhm.
Income is my sort of out, so that I've got age on the X, income on the Y.
Oh.
Income is skewed there,
Okay,
and
I
so
see.
that's what's.
Okay.
If it was the opposite, if it was a negative skew, we might get something that looked wide at the bottom and sort of increasingly narrow towards the top.
No, that makes sense. I wasn't looking at the actual distributions. I was like, how could you tell that from looking at just the plot? But
Yeah.
I see the distributions now.
Yeah.
Thank you.
All right, so if we have heteroscedastic data, if we have violation of homoscedasticity, it's not fatal, it's not the end of the world, it does weaken our analysis, okay? Then we'll see this again and again and again, not only thinking about like, do I have a violation, but what does this do to my model? if I have heteroscedastic relations, my parameter estimates are unbiased, okay? So that means my coefficients are unbiased. So whatever I get for the slope for this, so the expected value of y, or given a change in x, my actual regression coefficients, those aren't biased. Those are still fine. Problem is what we have is standard errors that are either inflated or attenuated, depending on sort of what our data is looking like. What happens if my standard errors start to get inflated and bigger? What does that do? Yeah,
Your test statistic goes down.
beautiful. That's right. So I take that coefficient, I divide it by the standard error. If my standard error is too big, my test coefficient or my significance test, my inference test is going to be too small. And so something that maybe should be identified as an effect probably isn't going to be. And if I attenuate it, if my standard error is too small, then what happens?
Oh, then it like inflates.
It increases. I've got too many type 1 errors, right? I'm sort of identifying too many things as effects when I probably shouldn't be. And what we see is generally, again, at least in the 2 variable case, if variability of my outcome increases with my predictor, kind of have that fan up shape. What that does is it inflates my standard error. If I get a pattern where it goes sort of the opposite direction, it's big at sort of the start and then sort of tapers down, it sort of it can attenuate that standard error. So again, being able to look at your data, seeing what's happening and think about what's maybe going on or what are the likely effects of this. If I'm just interested in a point estimate at a parameter, how much expected change in y should anticipate given a change in x, I have no worries, right? But if I'm actually interested in the actual test of those coefficients, now all of a sudden I've got a problem on my hands, or a potential problem on my hands. Okay. So we're going to look at our homoscedasticity, at least in initial screenings, through our inspection of bivariate plots, and then when we get into our actual regression models, we'll look at our residuals. This is really what we're worried about, but if we see something in the bivariate plots, that's probably giving us a signal that we're going to have an assay later on as we move forward with stuff. Homogeneity of variance with our grouped data. So we last semester used Levine's test. Now sometimes when we get into multivariate models, you don't have a Levine's test, or there are different types of homogeneity of variance you're worried about within groups and also between groups. Levine's test is just a within groups. What we can use is fallbacks on our F max ratio. F max is simply calculated as the variance across the largest and smallest cells in your group. So if I have a group-based design, and we'll get into this and use this when we get into our repeated measures ANOVA, we're going to have between groups, and then we're going to have within groups. What we can use is that F max ratio to say, okay, what's my smallest variance? What's my largest variance? And then just divide the two, okay? If I've got a balanced design, again, cell sizes are within 4 to 1, which seems not that balanced, but statistically balanced enough. If you have X max, so less than 10, you're doing pretty good. But if we start to get unbalanced designs, then much smaller F maxes can start to come into play, inflate your type 1 error, particularly if your variance is smallest in your largest cell, because that's going to carry so the amount of weight and determine your overall error variance, right? So we won't get into this with the regression, but put this in the back of your mind for when we get into repeated measures designs, because this will be an important part of the screening. Okay.
So you find F max by dividing the largest by the smallest?
Mm-hmm. Yep. So I've got, let's say I've got group 1 and group 2 time 1 time 2 and time 3. We've got a 2 by 3 repeated measures or mixed factors ANOVA design, right? What I would do is I would look at, for the group within cells, whereas my largest variance divided by my smallest, and the same thing here, and then the same thing here, and just look at those F max ratios to see if anything's way out of whack that I have to be concerned about. All right. So solutions, if we do have heteroscedasticity that we need to address, transformations can help. If we're getting heteroscedasticity because we've got skewed variables, going through running a transformation, bringing that in can be helpful in that it we'll fix that, make that data a little bit more amenable to the types of analyses that I'm working with, and then fixing stuff down the road. So transformations is something we think about. We can also run analyses that account for violations of homogeneity of variance. Okay, we've got options for some robust estimators that we can use that are different than our ordinary least squares that do an okay job of addressing violations of homogeneity. And so that's a possibility. You can also use more stringent alpha level, depending on the pattern. If you're seeing something that you're expecting to produce an underestimation of your standard error, what you can do is this said, well, I'm going to run tests at alpha 0.01, 7.5. You don't see this a whole lot, but I mean, it is something that you could do, right? If you were had concerns about something, okay? But probably transformation or just using a different estimator is probably going to be your best bet. Okay. So things like weighted least squares, things like that are better at addressing heteroscedasticity in your residuals and things like that. Questions? All right. This I think finishes up thinking about multiclinearity and singularity. Okay. Multiclinearity, this is going to be high correlations between my variables. Rule of thumb, about 0.9. If you get anything in that vicinity, like you have redundancies in your modeling, you should not be there in the first place. But if you look at text, they'll say around 0.9. Singularity, this is multiclinearity on steroids, where basically variables are redundant and they're a linear combination of two or more. Essentially, you have less information in your model than you think you have, right? This is singularity is basically a correlation of functionally one, right? In terms of matrix algebra, this is essentially what you're asking your model to do is essentially divide things by 0, which causes problems. Okay. For collinearity stuff, basically what we've got going on is I've got 5 variables in my model, right? But what actually I've only got 4, because maybe 2 of those are just identical to one another, right? If I know what one is, I automatically know everything about the other one, and so then it's not a useful variable. Okay. When we get into the actual matrix algebra of all this, did anybody take a linear algebra course? Do you remember much from it?
A little bit.
A little bit, yeah. I just got a taste of it in my multivariate class. I've never had a linear algebra course, but basically everything that we're doing here is all matrix algebra. And if we have a very simple sort of matrix here, right? So we've got 1 and 2 and 4 and 8. Do we have unique variables here or unique information here? No, right? There's a linear transform of, right? If I multiply this by 4 and this by 4, that by 2, that by 2. It looks like I have 2 variables. It looks like I have 2 observations and 2 variables there. I don't. It's the same thing, right? And so what happens when we go through what we've got a situation, when we're talking about matrix algebra, we would say that we have a matrix that's not full rank, right? And so what happens is if we go through and pull determinants of this matrix, which are sort of basically sort of capturing the variability in that sort of matrix of scores, we get something that's very close to 0. Okay. I won't force you to do matrix algebra. I had to do matrix algebra in my multivariate class. Cut it out. I feel like we've got more important things to discuss than making hand crank and multiply matrices and things like that. But do know that this is essentially what's going on, right? You're telling your model, hey, we have this information, this much information, when in fact you don't, and it's going to go through and cause problems. Essentially what's happening is our standard errors start to get unstable. Okay, they're going to jump around a whole lot, sort of depending on small deviations in our data, and we don't want standard errors jumping all over the place. Okay, so straight collinearity, we can examine this through bivariate correlation. We can just go through, run a correlation matrix, and just eyeball and say, hey, how closely are our variables related to one another? Okay, now in psychological science, all our variables can be related to everything else. Remember, our most efficient and most parsimonious models are going to be if we were to have predictors that are all orthogonal to one another. each one of these things is contributing a different piece of the pie. It's not realistic for the types of analyses that we do, but what we don't want to do is throw in a bunch of variables that just are all sort of basically measuring the same thing, even though the measures all have different names, but in actual fact, it's all capturing the same stuff. Okay, so bivariate collinearity, pretty easy to detect, but if we have collinearity with multiple variables, this is harder to identify. What we can see, particularly within the context of multiple regression, is that it's not, I could look at my correlation matrix and no individual two variables are highly correlated with one another. But if I start looking at the combination of variables, the combination of these variables perfectly predicts another variable. And now all of a sudden we've got something that you might not catch immediately, but what happens is it's going to cause problems with our model. Okay. And so the way we go through and detect this multi-collinearity is what's going on in the background of your analytic software is it's taking the squared multiple regression of one predictor regressed on all your other predictors. Okay, multi-collinearity is an issue among your predictors. Okay, now if you got like a redundancy between your predictor and your outcome, then that's problematic because you're measuring essentially the same thing. But from a statistical standpoint, we're worried about collinearity among our predictors. Okay, and so what SPSS Stata is doing when it's going to give you some of these indices of collinearity, what it's doing is it's taking X1 and regressing X1 onto X2, X3, X4, X5, right? And if I've got an R squared of 0.95 when I regress my first predictor on my other four predictors, that means there's too much overlap in there. If the combination of my other four predictors almost perfectly predicts my my last predictor, there's too much stuff going on in there, right? And so what we'll see is if we get a high squared multiple correlation or a high R squared, suggests we've got too much overlap with our target variables with my other predictors. Okay, and so this is a really handy way to go through and say, even though if I look at my bivariate correlation, I might see not anything that's super highly associated with anything else, but then I look at my collinearity diagnostics and I can say, nope, some combination of these variables is almost perfectly predicting another variable. I've got a problem in here somewhere. Okay. So some different metrics we'll go through and take a look at with the detection of collinearity. One is going to be my tolerance. This is just one minus my squared multiple correlation. Okay. For each one of my predictors. And so if I regress, say I've got four predictors, right? And so I regress X1 on X2, 3, and 4, and then I regress X2 on a 1, 3, and 4, 3 on a 1, 2, and 4, and 4 on a 1, 2, and 3. And I go through and I get an R squared for each one of those models and subtract it by 1. This is going to give me my tolerance, right? So here, tolerance values less than 0.1. Typically indicative of something we would flag as problematic levels of collinearity. Okay, and that makes sense. If I take 1 minus an R squared of 0.9, that gives me about 0.1 to problematic. Okay, but remember that anytime I give you a general rule of thumb, that's all it is a general rule of thumb. It is not a bright line situation. If you get anything at tolerance level that's even in the vicinity of 0.1 or smaller, you've got problems. Basically, you're measuring the same thing multiple times and trying to throw it in a model and call it something different. Conceptually, there's a problem there. You need to take a step back, figure out what's going on with your stuff. Okay. Another metric, and this is all sort of based on the same information, right? So it's not giving you unique information. It's just giving you a different way to look at it. Same thing. Like we talk about, p-value doesn't give you, or your base factor bound, or your BFB or your S value doesn't give you anything unique because it's all based on the p-value. It's giving you a different look. Same thing with your VIF. This is your variance inflation factor. This is going to be 1 divided by your tolerance. Okay. But if we go through and take the square root of that variance inflation factor, giving us an idea of the extent to which the variance of a coefficient is inflated as a result of my collinearity. Okay. So if I've got a VIF of 9, it's telling me that the standard error, my coefficient for that predictor is about 3 times the standard error would be as if I have a problem with collinearity there, right? So again, telling me with VIF I can get an actual idea of like, how big of a problem is this? Like, okay, well, I got a VIF of 9, like 3 times, my standard error is, the variability of my coefficient, my standard error is about 3 times what it would be is if I didn't have a bunch of stuff in my model that was hugely redundant with everything else, which suggests to me I should probably reevaluate my model and see what I can pull out of there, because what I've done, it's a kitchen sink approach, right? If I just throw a bunch of stuff in there and try and see what happens, what can happen is I can actually undermine tests of my actual coefficients. Okay. So again, PIF greater than 10, indicative of problematic collinearity. But again, if you get anything even close to that, like, you should be very concerned and need to go back through it and sort of conceptually say, what do I have in my model? What did I think I measure? What did I actually measure? How does this all work together? All right, so now most statistical programs have a sort of tolerance threshold before they'll just return you an error. Usually it's 0.1 to 0.001, right? I mean, but with the type of, you should never even get in the vicinity of that, right? It's actually pretty hard to get an OLS regression model to crash, but you can do it really easy in like an SEM, just based on an extension of that. Like, you'll get non-positive definite errors and things along these lines, right? So it's rare that this will literally make the whole thing blow up, so it'll tell you something, but you should very much identify the conceptual redundancy before you would even get in the vicinity of your model falling apart. You have an idea to sort of kind of understand what's going on with this. So solutions for our collinearity. If all we're trying to do is just predict an outcome, if we're just trying to maximize R squared, then we don't have to do anything about this. Okay, because remember, our coefficients, if we have collinear data, my coefficients are unbiased. There's nothing wrong with my coefficients. It's my standard errors get out of whack, jump all over the place. So if all I'm trying to do is predict revenue for next year for my business, who cares, right? That's not what we're ever trying to do, or rarely trying to do in psychological science. And so it probably is an issue, right? What we want to do is go through, check for errors in proper coding in your data, make sure that there's nothing else, nothing going weird on in there. This is the big thing. See if I've got predictors that are made up of other predictors. Okay. If I find that I've got a scale total, let's say I'm looking at, basically give me a construct. What's that?
Trauma.
Trauma. Look at it, like, he's gonna go to somebody else, so I'm not just giving trauma stuff. You just say
Sorry, it's on my mind.
give me something else. Give me something else. ADHD, okay. So I've got a total ADHD score, right? And so you'd be like, boy, what I really want, but I'm interested in looking at attentiveness and hyperactivity individually. But then I'm also interested in overall severity. And so what I've got is I'm trying to predict some scholastic outcome with hyperactivity scores, inattentiveness scores, and then also total ADHD scores. What's going to happen is you're going to crash your model, because your total score is made up of composite the other two. And so if I know what this is and I know what this is, then this is redundant, right? And I can do this. And so this is, if you just like to play around with data and sort of prove things to yourself, right? Like, you can generate a variable, a random variable, and then generate another random variable, and then add those two columns together. If I look at and call those variable 1, variable 2, and variable t, if I look at the correlation between variable 1, variable 2, and variable t, are any of those variables correlated with one another individually? Nope. There's 1's random, 2's random, and then 3, even though it's the sum of those other two, in the absence of the other one, I don't know what the thing is. So that all 3 of those variables are uncorrelated with one another. Okay. But if I go through and I put all 3 of them in a regression model, it'll crash it. Okay. So again, one of those interesting situations where if I can go through and look at my bivariate correlations, I look at my correlation matrix and not see anything problematic at all. And now all of a sudden I've got huge problems in my data, usually things going on with this. Okay, so just sort of be mindful about things and sometimes it won't 100% crash it, But I've reviewed papers where people are sort of doing, well, we'll look at this score and this score and this score, and I can't do that, that's. And then what you'll find is like, none of these are actual, predictors in the model, you're like, well, of course, because they're all sort of sitting on top of one another. Yeah,
Sorry, can we get one more example?
one more example
Yeah,
of,
just one more example of the crash, what causes the crashing,
yeah,
one more like real life example,
so give me a construct that you're interested in.
victim credibility.
Victim credibility, right? So let's say you got a measure of victim credibility that is composed of like different subscales, different components of sort of credibility, like, I don't know, like maybe how this person looks or sort of, and sort of like their sort of language ability or sort of things along those lines. And the total score is made up of the sum of those individual subscales. That's what will happen, right? So it's very literally mathematically, if I take A plus B plus C and I get a total score, and I try and throw all those in the mix, you'll have problems.
Okay,
What is the solution if you do want to go down?
Well, you shouldn't, because they're redundant. So you don't do that, right? So what you would do, you sort of like, you want to think about like, in sort of in Mace's example, well, I don't actually need that last score, because if I have inattentiveness and I have hyperactivity, I already know what the total is, because the two of those together is my total, and so it's redundant information. There's no reason for me to. It's a nonsensical question. Your question is not nonsensical. In the model, it's nonsensical because we don't. We've already. If I know this and I know this, I already know this, so I don't need to have that in the model.
So just do two.
Yep, let's do two with that.
or
Same.
just do the total. if you're
Or
not
just do the
interested.
total, if you're not actually not interested in sort of hyperactive, same thing, like sort of again, because Mesa opened the door for me, we'll talk about trauma stuff. I think we got like 4 PTSD clusters, right? I wouldn't want to look at sort of all 4 PTSD clusters and then PTSD total, because I don't. I need to make a decision. Am I interested in the clusters, or I'm just interested in PTSD as a whole? Which one do I want to look at? All right, delete redundant variables, right? Like, so this is what happened if I'm interested in, I've got a self-esteem measure and a neuroticism measure, right? And what I find is those two things are like super correlated, and they're not actually different things. They're the same thing. I need to choose which one of those I want to go through. Probably it's going to be the scale that's got better psychometrics, better established things along those lines. What I can do is, if I have collinear variables, I can sum or average those. This is, if we're just working with regression, this is a thing to do. These last two things are things to do. We've got structural equation modeling techniques and latent variable models that, if this is my issue, I've got better ways of handling this. But what I could do is, if I, let's say, had neuroticism and self-esteem, and I really wanted to have both of those scales in there, I could just take the average of those scales and just do that. There's problems with that, because now I don't know what construct I'm measuring. I have scores, but I don't know what those actually mean. But you could do that. So what we would normally do, the better way to do this is just create a latent variable. If those are the things you can say, these are two things that are high, these are 2, 3 variables that are highly representative of this construct. And we just model the construct in a latent variable model and then look at that. We're not going to worry about that here, but back in the day, before people had access to these types of programs, this was something that you might use, or using a principal components analysis to create component scores. Again, this is the half-assed version of a latent variable model, where we take a principal components analysis and like estimate composite scores based on a set of predictors, and then use the observed values to then sort of work into a thing. Neither one of, like, if this is your issue, regression is straight OLS regression is probably not what you want to do. There are better ways to go through and do this, but historically these were ways of dealing with collinearity stuff. All right. Questions about collinearity, how we go through and think about things, so what's going on. Again, this, like almost everything else we're going to be talking about, is a conceptual question. I want to understand like what's actually going on, not just that I have a high correlation. that should be the trigger to start thinking about what do I have in my model? What am I actually measuring? Irrespective of what the scale label is. And how does that relate to other things in my model? All right, questions? Who's up for a statistics haiku? That's pretty exciting, right? All right, so thinking about our regression, some basic assumptions with our regression, okay? First one, we're assuming for our OLS regression that our predictor variables are X's, okay? Are fixed, non-random variables measured without error with a variance greater than 0, okay? There's a lot to unpack here, but we'll get back to this.
And you said this is for the OLS?
Yep. For our ordinary least squares regression, like our standard regression that we all know and love and occupies 95% of the models that we'll see. Okay. We're also assuming that our errors, our residuals, are normally distributed. Okay. We're assuming that the variance of our residuals are constant for all values of X. Okay. So for any possible value of our predictor, we're assuming that our errors are equally distributed. Okay, this is our homoscedasticity assumption of our residuals. I'm saying this: the distribution of the variability of my residuals should be pretty much the same. Doesn't matter if I'm talking about low end of the predictors, high end of the predictors. That should remain constant. Okay, in statistical notation, I can say the variance of my errors is equal to some value. We're assuming that our errors are independent. Okay. We're saying that so whatever residual, whatever error I have for Haley is independent of whatever our error I have in the prediction of Gabe's scores is independent of the prediction of whatever I have in terms of my prediction of Johnny's scores. If I start to violate this, then I've got problems with sort of estimation and lots of different things. Okay. We can refer to this as autocorrelation if you have a repeated assessment. If you have nested data, you can talk about spatial autocorrelation. We're just wanting everybody to be separate and equal from everybody else. Every observation is an independent observation, unrelated to other observations. These last two, we are assuming that our errors are uncorrelated with observed values of X. Okay. What I'm saying is that I'm assuming that the value of the predictor that I have is not related to how much my model has missed on me, right? We're also expecting a value of error in the population is equal to 0. Okay, that says if we were to sort of run this model in the population, the average of all errors would be equal to 0. We've got some on this side, some on this side, everything sums to 0. Okay, now these two assumptions are noted in red text. That's because we can't test this. There's no way to test these or look at these. These are true by definition. If I'm running an OLS regression, these two things will be true, just in the way we calculate our estimates. Now, they very much might not be true in real life, but these will both be true by definition based on how we run our model. So we've got some conceptual issues to be thinking about here. There's no way to actually test these. From 1 to 4, we can go through and actually test these with some of the data that we collect. So if we go through and we think about our assumptions, different combinations, and this is more just to give you language and things. If you run into it, it's just in methodological data, you'll kind of understand, so it should ring some bells. My regression model will contain the best linear unbiased estimates. We call these our estimates. We say our estimates are blue when assumptions 1 and 3 to 6 are met. So if I have fixed non-random variables, I have homoscedastic errors, independent error of each other, independent error of my observed X0 population. I have the best linear unbiased estimates. That means sort of the best combination of my best linear combination of my predictors in predicting my outcome, and those are my best predictors of my population coefficients. Okay. So that's if you see someone say like, "Oh, my estimates are blue," and then best unbiased, best linear unbiased estimates. If my residuals meet assumptions 3 and 4, I'm gonna say that my residuals are independently and identically distributed. Okay, my residuals are IID. Okay, it means that if I go through and take a look, the pattern of my residuals are normal and they're independently, they're normal and identically distributed. So they're going, I don't have heteroscedasticity, things along these lines. Okay. Number 2 here, the normality of error is required for unbiased estimation of my standard errors. Okay. So this starts becoming important for my testing, my hypothesis tests, formulation of confidence intervals. If I have non-normal errors, what happens is that throws my standard errors off. And now all of a sudden my tests of those individual coefficients start to become off base. My confidence intervals start to get wonky. Most of the stuff that we do in terms of this regression screening is not the coefficients that we're worried about so much, it's the standard errors. Okay. So just keep that in mind as we're going through and working through stuff. Okay. So as we're going through and we're working through these regression or these diagnostic techniques, questions that you should be asking yourself, are the estimates that I'm getting in this model unbiased estimates of the actual population? Okay. And then 2 are the estimates of my standard errors and mean squared residuals unbiased, right? This is an estimation issue. This is a testing issue, right? I can have situations where my coefficients are unbiased, but my test of those coefficients aren't, because they are lacking standard errors, right? Usually I don't think that, I don't know if there's any situation where we run into where I have biased estimates, but my standard errors are fine. It's usually the standard error thing that starts to become problematic. Because this impacts our tests, this impacts our conclusions about sort of what effects we have, what we don't have, and so this starts to become important. Questions about this, and we're going to walk through each one of these assumptions, talk about them a little bit. Dog.
Such good data. Yeah.
They're good statistics too. My dad wouldn't get that joke. All right. Okay. First thing we're going to do, talk about violation of our fixed effects. Okay, our assumption 1. We say predictor variables are fixed, non-random variables measured without error with variance greater than 0. That's a lot of compound stuff, so on top of one another. So let's start breaking it down. Fixed effects. We're saying our predictor variables are fixed. Okay, fixed non-random variables. Fixed effects model, we talked about this a little bit when we were talking about correlation. We assume that our predictors have specified values sampled systematically with all possible relevant values captured in all subsequent replications. Okay, for a fixed effects model, my variables are not random variables. My sort of values are chosen specifically to capture all relevant values within whatever predictor that I've got. Okay, so I'm not just going out and saying, hey, opening the party to whoever wants to come in. I'm sending out invitations and saying, I need X number of these values, 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 X number of these values. And in any replication that I go on to go through and produce, all of those replications will contain the same sort of values within the model. Okay. And because of this, our fixed effects regression makes no assumptions about the distribution of our predictors. And this makes some sense, right? If I'm getting this many values and this many values and this many values and this many values, what's the distribution of my X look like? What's that?
Whatever we've decided it to be.
Whatever we've decided it to be. If I've got equal values, equal representation of all relevant values of my predictor, it's just flat, it's square, right? It's for sure not normal, right? And so for our fixed effects regression, and you'll see people talk about this and sort of misinterpret this, they'll say, well, distribution of my X's my predictors doesn't matter because there's no assumption of normality in my fixed effects regression model. Absolutely true. But we also, so the variable that you've got that's all wonky is probably not a fixed effects variable. What it is, it's a random variable that just has a crappy distribution, right? So for a fixed effects model though, and this starts to get into regression's origin again in sort of old school experimental stuff, like is basically if you're running an experiment and you're like, these are my conditions. These are the only conditions I'm interested in. Anybody who would run a replication on this would only have these conditions. You've got a fixed effect situation, right? And so this is great. We don't have to worry about the distribution of our predictors if we're actually running a fixed effects model, right? And so here I've gone through and I've got my sort of jar of jelly beans or gumballs or whatever, and I've selected sort of a specific number of every single color. Those are all in there. All colors that will ever be in this model are the same colors that are in this model. I've systematically gone through and selected it, right? What we actually do when we go through and we collect data is we're actually doing this, right? We go through and we just say, who wants to be in the study? People come into the study and then I measure those predictors and I'm going to get some sort of distribution, right? This is not what a fixed effects model is, okay? So what we're doing, even before we start out with, we've got a violation in just the way we go through and use this model and conduct this model. What we've got is we've got a random effects model that we're trying to estimate as a fixed effects model, okay? And so again, this fixed effects model is almost always violated unless you've done have some really elaborate sampling scheme where you've gone through and done this. But the good news is we can still use this fixed effects model with random variables so long as the variables in our model are multivariate normal, okay? So now, even though technically within regression, we have no assumptions about what the distribution of our predictors look like. But as soon as we violate the fixed effects assumption, now all of a sudden we do have to be concerned. Model's still fine so long as our predictors are multivariate normal. But if they're not, I end up with all sorts of things turn into a mess. Okay. So what we're going to do is, so wanting you to recognize if this comes up, people are like, oh, regression doesn't have any assumptions about the distribution of variables. Yep, sure. Unless you're actually running a random variable model. And if you are, now all of a sudden you have to be concerned about this. Okay. Yeah. We'll get into that. Yeah. Okay. It's really hard to test specifically, but under two conditions, if all our variables are normal and all of our bivariate relations are linear and heteroscedastic, we're assuming multivariate normality. Okay. All right. So this is the fixed effect non-random variables thing. Okay, we're saying also we're assuming that our variables are measured without error. When does this happen? Never, right? And so if we go through, but it's an assumption of our regression model, right? If we think about classic testing theory, we're saying, so this observed value that we have of X is some combination of true score variability and error variability, right? I go through, I measure, Lindsay, give me a construct.
Eating.
Eating what?
Binge eating.
Binge eating, okay. So I give someone a measure, give a sample of measure of binge eating, right? Those scores, I'm interpreting those scores as severity of binge eating, right? But in actuality, those scores are going to be some proportion of binge eating, like the actual true construct, and some stuff that's error variability, right? It's error variability because it's going to be due to sort of picking up other constructs that aren't exactly eating binge eating stuff. There's going to be related things that get pulled in, and then it's just going to be random stuff that's going on, right? So my actual observed scores that I have are some portion of true score and error. Now, if you've got a really good psychometric measure, hopefully most of it's true score and it's a little bit of error. But this is where it starts to get real dicey when I just make up my own measure for my own study, when there's no psychometrics to tell me that I'm actually getting at what I think I'm getting at. This is why it's important to sort of go through and make sure and tend to our measures, make sure that we've got good measures, okay? So what happens, because we're in violation of this, if I've got measurement error in my outcome, this doesn't bias my parameters, but it leads to inflated standard errors, okay? So if I've got a dirty outcome variable, right? It's just kind of ugly and it's kind of getting at what I think it should be getting at, but it's got a lot of other stuff going on in there too. It's not gonna necessarily bias my coefficients for my predictors. But what it's gonna do is it's gonna increase my standard errors. And if my standard errors are bigger, what does that mean for my model?
And it's bad.
It's bad, it is, right? What happens to my power as my standard errors go up? It goes down, right? I need more people. If I've got dirty measures, I need more people to go through and test those effects because I got a whole lot of static and junk in this, right? If I've got really good measures, really precise measures, it reduces my standard errors, which makes it a lot easier to detect the things I'm hoping to detect, okay? But if I do have measurement error in my predictors, now I do have biases in my parameter estimates. Okay, so if we think about here, let's say this represents my coefficient of my predictor with some outcome. Okay, this is my regression coefficient. This regression coefficient in classic testing theory is going to be a product of my population coefficient, the actual true value, multiplied by my reliability here, okay? Now, if I have perfect reliability, if I have no error in my measurement, then I've got my population coefficient multiplied by a value of 1, which is unbiased, right? What happens, Abby, give me a reliability value that's less than perfect.
Like 0.7.
0.7, okay. If I take this and multiply anything by a decimal, what does that do to my outcome? I multiply it by a decimal. Makes it smaller, right? And so what we can see is that if I'm measuring my predictors without error, I'm multiplying my population coefficient here by 1, and then my parameter is fine. But as soon as I start to introduce measurement, or my reliability coefficient here is not 1, it's some decimal figure. And so what happens is it starts to attenuate my regression coefficient, makes it too small, right? So what I'm doing is I'm systematically underestimating my regression coefficient. And as that reliability goes down, as I get sort of poor and poor and poor reliabilities, the impact on my estimation gets bigger and bigger and bigger. Again, what we're seeing here is we've got attenuation of our estimates based on non-perfect reliability. Someone's about to raise a hand or have a question.
Yeah, I was just wondering if you couldn't follow what you said A was, or like what you were calling it, reliability.
I'm sorry, what's that, Kate?
Alpha, what did you call alpha?
Alpha, just my reliability. It's just a general for reliability, right? So, I mean, it's not necessarily coefficient alpha. It could be test, retest, reliability. It could be any measure of reliability. As my measures become less reliable and have more error, what it does is it's functionally attenuating sort of my the calculation or the estimates of my coefficients in my model. Okay, so this measurement error is going to increase residual variance, right? And it's going to attenuate my overall R squared for this. Now, when we start to get into multivariate space, the impact of error is kind of unpredictable on individual coefficients. It can, it's not just the error of my one predictor, but it's combined with the error in my other predictors and does some weird stuff, right? So in the bivariate case, this is true. When we get into multivariate space, what we end up with is just bias in our predictors, but generally attenuation in our model R squared. Which this isn't so bad because this generally isn't the thing that we're focusing on with the types of models that we run, but sort of noting that anytime I've got measures that are not good or reliable or psychometrically sound, I'm throwing sand in the gears. Okay, I'm making life harder for me. I'm reducing my power. I'm throwing biases in my estimates, things along those lines. This is where, through all this stuff, methods and statistics kind of come into play together. They're not independent, right? So thinking about, and we should always be thinking about developing the most powerful studies that we can. Sample size is important, probably the biggest thing, but also thinking about having good measures, psychometrically sound measures, starts to help me in the long run because it reduces error and gives me more precise estimates and sort of doesn't result in attenuation of my parameters or my coefficients, R squared, increasing standard errors, things along those lines. And this is really sort of one of the big things. You know, if you're wanting to look at something that no one's ever looked at before, and there are no measures of it, and like you for your study have to create your own measure, then that's what you got to do. And that could be a contribution and a cool thing, but just be thinking about like, hey, I have to be very careful and mindful in terms of how I'm developing these scores. Because any error I'm throwing in there is going to just grind up the gears in my model. Questions about this? Right. Also, variance greater than 0. Why do I need variance greater than 0 in a predictor? Yeah, otherwise I have a constant and my model's not going to like that, right? Okay. We're comfortable with this, right? So basically, assumption 1, we always violate like 2/3 of this all the time. What we then need to do is say, okay, this is kind of our original sin. Now we just need to go through and make amends and kind of address this in other parts of our model to go through and make things okay. All right. Assumption number 2, our errors are normally distributed. Okay. This is a basic underlying assumption of my tests for values of my multiple, for the test of my multiple correlation, my regression coefficients. If I have non-normal errors, this will start to cause problems for the tests of my coefficients. Okay. Here, again, and this is easier to see in just the relation of X and Y here. But what we see is as my X increases, my Y increases, I've got a sort of linear relation here. But for any value of X, if I were to go through and take a look at this, my scores are relatively evenly distributed, and I'm assuming that they're normal, right? Again, so I've got this there. Again, X and Y, if we turn a Z value up here, we can see that they're kind of clustered up around that regression line and then kind of spreading out, right? This is what we're hoping happens when we go through and take a look at our residuals. Now, if I have non-normal errors, this can produce all sorts of different issues. What we generally see is this is, or can often see is this is sort of maybe a sampling strategy, or could be a problem with sort of actual distribution of things that we're looking at. Okay, so if I go through and let's say I'm looking at the relation between depression and life satisfaction, right? And what I've done is I've only sampled people who are struggling with severe levels of depression. Okay, what I might have is something that looks like this, right? Now, if I go through and I take a look at so my regression line, here's sort of my prediction line, or my my mean value. What I've got is if I'm looking at the relation between depression and life satisfaction, I kind of hit a floor effect, right? Because I just have a bunch of people who just aren't doing well. And if I've got a bunch of people who aren't doing well, what's going to be their ratings of life satisfaction? It'd be real bad. And if I bottomed out on the floor, if I do have errors, where those errors kind of almost have to come from? Higher levels, right? And so when I miss high, right? So what's going on is in this situation, if I go through and I look at my residuals are for sure not normally distributed, right? They're all positively skewed. I'm doing pretty good. For the most part, I've got people who are really depressed, who are reporting really low levels of life satisfaction. But I'm going to occasionally have people who are reporting pretty severe levels of depression, but also for whatever reason, maybe they're just resilient, things along those lines, be like, oh, you know, things are okay. And so when I miss up high. And so what I've got is a situation because of the sample I've chosen to select to collect. What I've got is essentially what we're dealing with is a floor effect here. Okay. Other thing too, if we take this and okay, so yeah, our floor effect, when our regression model is wrong, our observed outcomes systematically exceed our predicted outcomes. And so what we've got is all those errors are trending towards sort of one direction. Okay. Same thing here. And again, I don't know where I got it. Wasn't my example. This was someone else's example. But heroin use in children, right? Heroin use in children should be pretty low, right? Like we should expect no children to be using heroin, hopefully, right? But if we go through and we look at age, as sort of age increases, we are going to have some people who are using heroin. And if we have people who are, we're probably going to expect that they're not. And so everything's kind of going in terms of our residuals. We're predicting no use. So if people do have use, my errors are all going in the same direction here, right? So again, what we've got is sort of working with this floor effect where we've got some rare behavior that's not happening very often or happening very rarely. And so when we go through and we miss, we're not in this model, we can't predict that children are using less heroin than zero heroin. There's nothing else to go there, right? So when we miss, it all goes the one way. And so what we can end up is residuals that are positively skewed. People kind of seeing how this can happen. So if we have non-normal residuals, again, our regression coefficients are fine. Nothing wrong with our regression coefficients, but what we'll see is a depression of our standard errors. Okay. And if our standard errors are too small, then our tests are overly optimistic, right? We've got inflated test statistics, which means probably a greater number of type 1 errors. So not only identifying that we have a problem, but knowing what the consequences of that problem are starts to become important in applied work. We've got a small sample non-normality will also depress the standard error of my overall R squared. Again, this is less of an issue because we're rarely interested in whether our test of R squared is something that's not zero. There's stuff that comes up, but it's not a huge thing. Mostly we're worried about the impact on our standard errors for our regression coefficients. Right. One more and then we'll go through and break. Variance of my residuals is constant for all values of X. Okay, so number 2, we're assuming normally distributed errors. Here, this is our homoscedasticity assumption, right? We're assuming that equal conditional variance of errors is essentially what we've got going on here. We're saying that for every predicted value of X, we'll talk about it, it actually ends up my predicted value of Y. We're assuming that that the variability of my errors around every predicted value is going to have the same variability, right? So I'm saying that at low levels of predicted value of Y, that I don't have I'm pretty accurate at low levels of predicted Y, but as my predicted value Y gets bigger, my residuals fan out like that, or the opposite direction, sort of it comes down. Okay. Here, when we're talking about our homoscedasticity assumption, we're looking at application to our residuals as opposed to our observed scores. So here we've got sort of X and Y as just 2 variables, and we have constant error variance. We have a homoscedastic relation here. When we get into looking at this in our regression models, we're going to be looking at the relation of my predicted value to my residuals, right? So based on my model, predicted values of my outcome should have my errors across that should be constant. Okay. So again, sources of heteroscedasticity, again, measurement error, right? We've talked about that a little bit. And here, omission of my relevant predictors. Okay, so if I just look at the association between age and income, that's a heteroscedastic relation. X and Y are heteroscedastic, right? As age increases, variability in income increases. That's fine, and I should flag that when I'm looking at sort of in my initial screening. But that doesn't necessarily mean that I'm going to get a problem with my residuals. Okay, because in that model, if I go through and I add education into that model, Now what's gonna happen is what I might see is even though age and income are heteroscedastic, as soon as I throw education level in there and maybe some other variables, what happens is those other variables account for the increased variability. When I have those in there, my residuals are actually normally and identically distributed across the whole range of my predicted value because I've got the right variables in there. That's accounting for the heteroscedasticity. So this is another thing that starts to become important with our screening procedures. What we want to go through is go through and say, hey, in the bivariate situation, I've got sort of some heteroscedasticity here between these two predictors. But when I go through and I screen my residuals, it's actually looking like it's okay, probably because I have the right variables in the model and it sort of takes that stuff away, so it's not a big deal. Okay. So for if I have non-constant invariance, okay, if I have heteroscedastic residuals, again, regression coefficients remain unbiased, but my standard errors are biased in the direction of the relation of errors to my predicted values. Okay, so if my error variance is increasing as my predictor value increases, then I'm going to have standard errors that are too low. Okay, at low ends of my predicted y, very little variability, and things start to get bigger and fan out as things get as my predicted values get higher, my standard errors are going to be too small. Okay. The opposite thing happens if my error variance decreases as my predicted value increases. I've got an opposite cone kind of going this way. Now I've got a situation where I should expect inflated standard errors. And in this situation, if you've got heteroscedastic errors, this is maybe a time to go through and think about transforming or maybe using a robust estimator to go through and account for the fact that you've got heteroscedasticity in there. We won't worry about that for this in this class, but it's something to keep in the back of your mind as a solution. If I didn't want to jack around and try and address things with transforming my variables and introducing interpretive nonsense with that, I just go through and so like, hey, I ran this regression with an estimator for robust standard errors. It's called a sandwich estimator, which is fun. But we can go through it and sort of address that, but want to know that that's there. Okay. All right, cool. Let's take a break. We'll jump back into independent errors. Yeah, let's come back at we'll call it 3:35.
Oh, I just tell me about your iron.
All right. Questions thus far about some of these regression assumptions that we've been working on. Okay, some of it is going to be I didn't sort of pick this up. I don't think anybody picks it up like first pass back. Oh yeah, sure, that all sort of clicks for me, right? So go back through and sort of look at these carefully just so you have a good idea of sort of what we're doing and why.
I do have a question now. For like these models and running them through SPSS or Stata or R, what do you like? I've heard it's a lot easier to do it like in R compared to SPSS and the way, like, what's your opinion on that? Like, are they all pretty?
My opinion is the program you get to use the numbers is inconsequential. It doesn't matter. Like R's not running OLS regression different than SPSS or anything else, right? So a lot of that's personal preference and things along those lines. And thinking about like, so because things are moving towards R, like, do we maybe switch this over to an R-based course, right? My concern is now I've got to teach you content and sort of conceptual stuff on top of trying to get you to learn how to code R. And that seems like a nightmare that I am not interested. SPSS is fine because you can go through and pick down sort of menus and things along those lines. Really, and I hope like you sort of pick this up at this point, I could care less about where you're getting numbers from. And like, I actually don't care as much about the numbers as you understand where they're coming from and what they mean and things along those lines. So a lot of that's preference, right? I mean, I use SPSS forever. That's fine. I switched over to Stata because I got tired of SPSS making me pay for SPSS, and now I really like Stata. I've used R. I'm not competent with R. I have to get Johnny to help me like, hey, what's going on with some of this stuff. But I mean, it's a good program, and so like, but for the types of things that we go through and do, like the program you use, it doesn't matter at all, so. Nice to hear. All right, now, jumping into, assumption 4 here, we're assuming, independent errors, okay? And here, as we talked about before, we're assuming that our errors, or sort of the extent to which we're missing our predictive model is missing your actual observed value, is not dependent on anybody else in the sample, okay? Different ways where we can get sources of dependency in our residuals. We typically talk about this as autocorrelation, okay? Like this, we can go through and review, it's just me muttering curse words into the microphone. All right, we can get temporal autocorrelation, and this when you hear the word autocorrelation, this is usually the context it's being discussed in. If I have some sort of time series set where I've got the same person or the same set of people being measured multiple times, let's say, is anybody doing, I know several of you in your labs, sort of EMA types of studies, things like that? Anybody?
Not currently, but I have.
Okay, so basically we get a set of people, and so maybe my phone goes off multiple times a day and I just sort of log my mood or something like that, right? What we're gonna see in that type of data is a degree of what we would call temporal autocorrelation, right? So if I'm following Daniela, and your phone is just going off sort of at random times during the day to sort of log your mood, those time points that are closer together, the errors that we're gonna see in predicting your mood in time points that are closer are gonna be more closely related than sort of time points that are far apart, because you're gonna have changes and fluctuations in mood and things along those lines, right? And so what we've got is errors that are occurring closer in time to one another are gonna be more related to or closer to one another than errors occurring farther apart in time. And so what we've got here is a situation where we've got temporal autocorrelation with a repeated measures design. Okay. We can also have something called spatial autocorrelation. This starts to get into folks who do kid-based stuff, right? So Lindsay, or excuse me, Allison, Kate, maybe Mesa, if you're in schools and working and stuff like that, I'm looking at kids in a classroom in terms of some outcome, right? And so those kids, if I'm sampling multiple classrooms across multiple schools, those kids that are all in the same classroom are going to be more similar to one another than any randomly selected kids across classrooms. And so what we're saying is, even though no one's looking on anybody else's paper with this, we're going to start to see clusters of errors being more closely related than sort of others. And so here what we've got is what we call spatial autocorrelation. Okay. Now what happens, again, if we go through and we ignore this and we just use our regular OLS regression models, what we'll see is, again, our regression coefficients are unaffected. Our regression coefficients are fine, but our variance estimates and our standard errors are going to start to become biased and out of whack. What we see is we underestimate our mean squared error from our overall regression model and our individual standard errors. Those are much lower than they should be, because what we're doing is that model is capitalizing on the fact that if I know what Allison's error is, then I know what someone else's error is. And so what ends up happening if I just ignore this, things start to pop up as, oh, this is an effect, when in fact it's not. What we're just doing is we're capitalizing on the autocorrelation stuff. And so it can lead us to unwarranted conclusions about our data. Oops. All right, now in terms of independent error situation, this is going to be a situation where we can test for this, but really this is going to be a situation where it's a study design issue. If you're collecting data where you've got nested data or you've got a repeated measures design, you just got a design that the standard regression probably isn't appropriate for, right? And if you tried to publish something at that, like the reviewers would be, no, you can't do that. That's problematic, right? Now we're talking about going into something that's sort of a more, maybe a little bit more complex repeated measures design. Most of the time we're dealing with this in HLMs, hierarchical linear models, mixed effects models. There's about 7 different ways people go through and talk about this, but sort of data that's accounting for the structure, the inherent structure of your data. Okay, so again, this is not something that we need to be worried about unless I'm running a study where this starts to become relevant. All right, independent errors. Here where the assumption is that my errors are uncorrelated with the observed values of X. Okay. Here we're saying in OLS, uncorrelated errors are a direct product of just the math of estimating these models. We can't test this because this will be true by definition based on the estimates we get in our ordinary least squared regression. However, that doesn't our ordinary by definition this will happen, right? But that doesn't mean that this is actually happening out there in the real world, right? But what we can do is conceptually sort of take a step back and say this is probably not going to be an issue if I have a correctly specified model. Okay. And we would say that my model is correctly specified if I have for whatever I'm trying to do, all variables that need to be in the model are in there, right? I've gone through and I know my content area well enough to say that, hey, if this thing is an important thing in predicting this outcome, I've got it in my model, right? We've also not included irrelevant predictors. If something's not needing to be in there, is supposed to be in there, it's not in there, right? So we're not just throwing like whatever into the mix to see like, oh, does this predict? If it's not, doesn't need to be in there, we don't have that in there. And then we've got the form of the relation correctly specified. If these things are true, we would say what we have is a correctly specified model. And then our independent errors issue shouldn't be a thing. But there's no way to actually test this, okay? Now, if we get into sort of econometrics and things like that, in econ, people taken econ classes before? Okay, like if you get into econ methods, they start to get hypersensitive to this type of thing. Because for us, there's no causality, particularly for correlation stuff. We just say this thing holds a unique relation with this. So I'm not saying why it does. I'm just saying it. I mean, I might have ideas. Econ, it's much a more applied situation where we want to say this thing is causing this outcome. And so now all of a sudden, if that thing isn't causing that outcome, it's because of some omitted variable that we didn't have in there. Different disciplines will start to become more concerned about this. We typically aren't in psychology, but it's something that you should be thinking about just so that we don't have biases in our estimation. All right. So, and again, including relevant predictors, I can't test. There's no way to test this, right? And if I screw this up, what I can have is misspecification on all different types of aspects of things. So I wanted to think very, very carefully and intentionally about how we're building our models and sort of making sure that we have relevant information in there. Yeah. Also, we're assuming 0 population error. Ordinary least squares, that's what I was trying to say. The expected value of my error in the population is going to be equal to 0, right? So if I go through and I look at my residuals, I'm going to have some positive errors, some negative errors. My assumption is in the population, if I were to run this model in the population of interest, what I would find is that all my errors would sum to 0. Now, by definition, this will happen in OLS. It mathematically has to happen, but it doesn't. There's no guarantee that this will hold within the population. Okay. So some examples of this thinking conceptually. If I measure weight on a scale that's 5 pounds heavy, okay? So I'm going through and I'm measuring everyone's weight and sort of going through reporting it, and I run my model. So my population parameter, my intercept is going to be biased. Everybody's weight is going to be 5 pounds heavier than it should be, right? If I go through and I'm looking at, again, let's say I'm doing kid work and I'm looking at playground aggression, right? If I have kids who are generally not aggressive, it's going to be easier to track and code than if it's Lord of the Flies out there and everybody's punching everybody else. I'm going to like sort of miss stuff, right? And so what's going to happen here is that my error is going to be observed, my errors are gonna be related to my observed variable, like as occurrences of regression increase, my error is gonna increase, right? And so it's not gonna sum to zero here in the population, I'm gonna be off base, okay? So if we get this, and we have or sort of non-zero population error, we're gonna get bias in both our parameter estimates and our standard errors. So again, this is kind of a big deal. Fortunately, the impact isn't sort of terrible with this, likely. You know, it's most often gonna impact the intercept, right? So if I've been biased and so as sort of kids are hitting each other more frequently, I'm missing that. Sort of my base rate of how often kids are getting hit is gonna be too low because I've missed a whole bunch of stuff, so my errors are not zero, right? But that's generally gonna hit my mean value, which for my regression model is not typically what I'm actually sort of most interested in. So not generally as big of a thing. It's not something we concern ourselves too much with these models in psychological science, but something that you should probably be aware of and just sort of thinking about. This gets just back into precision of measurement and making sure we're using good tools, psychometrically sound tools so that we get the best estimates possible. All right, but again, this will happen if I go through and I sum up my residuals in OLS, they'll always be zero. By definition, they will. So I can't test this within my model, but it is an assumption that we should be keeping in the back of our mind. Okay. So thinking about how we go through and start to check this stuff out in applied settings. Violation of my fixed effects assumption is ignorable when my variables are multivariate normal. Okay. Kate, this is getting to your question, and we're going to assume we don't test it correctly because it's a complex thing. There are ways to go through and do it. It usually involves like SEM software and things along those lines. For our purposes, what we'll do is if each variable and all linear combinations of variables are normally distributed and homoscedastic, and my residuals are normally distributed and independent, I'm assuming that I can go ahead and ignore that fixed effects piece without any consequences for my model. Okay. So again, we want to go through, this is going to be univariate checks and then checks on my residuals to make sure that even though we know we violate that first assumption, it's not going to have consequences for our estimates. Okay. My linearity assumptions involving normal and homoscedastic errors 2 and 3 here. What we're going to do is we're going to look at scatter plots of our standardized predicted scores by our standardized residuals. We're going to look at normal probability plots, different histograms. Johnny, this is where we get into QQ plots and PP plots and sort of all this type of stuff that you've been. It's always a winner. You correct it every time. I don't get to choose what things are called. That's what they're called. Get into it. They're exciting. So we'll get into some of these types of diagnostics. And then concerns with independent errors. This is situations where we've got sort of known design issues, right? This isn't something we're going to be too concerned about. There are ways to set this up to check this in your data, but this is just going to be like, how did I collect my data? Is this something that falls into one of these areas? And if not, we don't have to worry about it. All right, so 1, 2, 3, and 4, we can go through and check in our data. 5 and 6, we can't. Doesn't mean it's not important. We still want to think about these. It's just not something that we can physically check with the observables that we have. Questions? All right. So what we're going to do is we're going to go through and sort of use a hypothetical set of data to go through and start walking through what these assumptions look like, how we would go through and approach looking at this and what data sort of might start to come up. So here what we're doing is we're going to run a model where we're interested in the unique associations of psychological flexibility, reward responsiveness, behavioral inhibition, and willingness to utilize social resources on perceived social support. So we've got people's level of social support, and each one of these things are all our predictors in this model. Okay, so for these data, my MSPSS, this is my measure of perceived social support. AAQ, this is psychological flexibility, this is just sort of your ability to kind of roll with punches and sort of things along those lines, not get too rigid about things. We got the BAS reward, this is reward sensitivity. Something good happens to you, how much does that drive you wanting to do more of that thing? Behavioral inhibition, right? This is sensitivity to punishment, to things along those lines. And then NOS is going to be our willingness to utilize support networks, right? So if I have social resources available to me, will I reach out and utilize those things? And thinking about these as all things that might predict people's level of perceived support. Okay, so simple regression model, we've got one outcome, we've got 4 predictors. I'm going to go through and want to screen this to kind of see what's going on with things. All right, so if I go through and write out my model, get used to writing these models out. Like, don't ignore that and think this is a not cool exercise. It's a very cool exercise, particularly as we start to go into and start working with moderation models. I'm going to say, okay, here's how I can go through, set up my coefficients and actually put together my predictive model, sort of using terms. Right here on the end, this is my error term. These are my residuals. This is going to be the focus of 90% of what we're up to with this. Okay. What's that?
Can you go back for 1 second?
Yeah,
B0 there, what would that?
that's my intercept. Okay. Again, what's my intercept? Johnny, what's my intercept?
When your X value is equal to 0, what your Y value would be.
My predicted value of Y when everything else is set equal to 0. Now, everything else set equal to 0 might be sort of a reasonable thing, or it might not be, right? These are all, I don't know if 0 is a real value on all of these scales. It might not be, right? But mathematically, that's what we're looking at, right? If everything is 0, what is my expected value? It's kind of our starting point. So going through and doing these screenings, what we're going to start doing is kind of just the raw data univariate stuff that's similar to what we've done in the past. We're going to look at accuracy, plausibility, missing values, looking at my univariate distributions, okay? Again, different than with our means-based analyses. With our means-based analyses, Daniela, were we overly concerned with the actual shape of our observed data?
More concerned, right? But it's means-based, that was the stuff from last semester.
Yeah, from last semester. Was it with our t-tests and our ANOVAs, did we need to assume that our actual distribution were perfectly normal when we were looking at that? No, right? Our assumption was the distribution of sample means, right?
Oh, yeah.
If the distribution of sample means is normal, then my actual observed distribution could be kind of funky and I wouldn't worry about it too much. Changes here, right? Because what we need to do is we need to do some multivariate normality in our data. And for multivariate normality, we need to assume that our data are at least reasonably normal and hold linear and heteroscedastic, homoscedastic relations with everything else. Now, if we start to get funky distributions, it starts to play tricks on us as we go through and take a look at things. So again, for our standard fixed effects regression, we have normality assumptions about our predictors, but because we always violate that and we're actually running random models, now we have to be concerned about what our distributions look like. Okay. Univariate outliers, extreme values, we're going to go through and take a look at that. And then we're going to look at the linearity and homoscedasticity of our bivariate plots. Okay. Again, this is starts to become important for our assumption of multivariate normality. Also looking for possible specification errors. Okay. Specification error, remember, is do I have a properly specified model? Do I have everything in my model that needs to be in there, right? And so if I start to see nonlinear relations and I'm trying to run a linear model, then I've got a misspecification because there's a nonlinearity in there, right? Now that nonlinearity might go away when you get other predictors in there. Same thing as with the heteroscedasticity. So it's not a make or break thing, but it's definitely something that should raise flags to say, as I'm going through and taking a look at my residuals, doing that stuff, does this problem go away or does it get a lot worse when we start to look forward to things? So again, primarily looking at my bivariate relations, because that relates to multivariate normality, but also sort of thinking about, are there things in the model that need to be in there that I don't have in there? So if I go through, take a look at, and we're just gonna do this real quick because it's gonna set up some of the other stuff that we're gonna look at in terms of the actual regression diagnostics. Here is and these are on those supplemental slides that I sort of sent out to you, so you've got this. Here are just my descriptive statistics for all the variables I have in my model. Remember, here's my model up here. Nami, I'll ask you, just because I did all this in Stata and you've been using Stata more, is there any concerns with my distributions here? What's happening? No, doesn't look like there's any problems here. These kurtosis values might look big, but in this program, a neutral kurtosis is 3. Mathematically, neutral kurtosis is equal to a value of 3. So Stata just actual puts that in there. SPSS automatically subtracts 3 from everything. So here we've got a little bit of positive kurtosis, a little bit of negative kurtosis. That's almost perfect. A little bit of negative, a little positive. So based on this, nothing looking too terribly wrong in terms of my distributions, right? For our means-based analyses, I'd be like, okay, looking pretty good, right? Well, if we go through and start looking at what those actual distributions look like, maybe I start to get a little bit more concerned. Maybe not concerned, but sort of there's notable stuff going on here. Here's my outcome variable. This is my perceived social support. So what's going on with perceived social support here? If higher scores are indicating greater levels of support.
It looks a little bit positive.
Is it positively skewed?
It's a negative.
Negative skewed, right? We're looking at the tail, right? So phenomenologically, so in terms of what are people actually telling us in this sample?
That as. What was our X variable?
So this is just a univariate. So
Oh, okay.
this is just social support. So what does social support look like in this sample? Based on this distribution. Well, this is just sort of everybody's social support score. Are people generally reporting higher levels of social support or lower levels of social support?
Higher.
Higher levels of social support, right? And we got this ceiling here where our modal score is the max value of 7 here, right? Like, so in general, we've got people who are mostly feeling sort of high levels of support, right? And then we very clearly have some negative skew, and we see here, that's a negative skew. It's not even 1, right? What do we flag as, oh, this is problematic? Our general guideline. 2-ish, right? So we're still way below, so what we would flag as problematic violation. But is that a normal distribution? No, right? It's for sure not, right? So just going through and thinking about like, okay, we have our benchmarks for what's problematic, but then what the actual data look like, it would be ridiculous to identify this as sort of approximately normal because it's very much not, right? So already we know that we've got an outcome variable that has a negative skew going on, right? Here is our AAQ score, our psychological flexibility. A little bit of positive skew, a little bit of negative kurtosis. It's a little boxy, but probably nothing too bad to worry about here. This is my reward sensitivity. Again, what's happening with reward sensitivity, Allison? Some negatively skewed, right? Not as bad as this necessarily, but it's sort of skew of -7, right? So you've got some negative skew going on there. Here is my behavioral inhibition scores. Those are looking okay for the most part. And then here's my willingness to sort of engage support networks, right? So here we've got things are pretty symmetrical, right? A little bit of positive kurtosis, kind of peaky here, but not too bad, right? So is there anything in this that would, sort of, I would immediately flag and say like, oh, hey, this is real bad, we sort of need to start putting on transforms and things along those lines? Probably not, but what you're gonna see, and if we're doing means-based analysis, would we be concerned with any of these distributions with a sample size of 355? Or 335? No. But what we'll see as we start to sort of move into our regression diagnostics, now all of a sudden funky things start to happen if we have data with these characteristics. It doesn't mean that we're necessarily not good, but we need to sort of start to recognize, like, okay, these features in my data are producing these types of things in my diagnostics. Okay, so we go through, look at our univariate. We won't go through and put together box plots just for the sake of brevity. But what we do want to go through is take a look at our stream values, linearity, and homoscedasticity assumptions. So here I went through and I produced Z values for all of my variables. Again, Johnny, take a look at this, and not that Johnny has special knowledge in it, anybody can get him in the max column, but like, are we seeing any concerns with problematic values in these data? What makes you say that?
A lot of our. Trying to think of the best way to say this. They're all staying below like 3 standard deviations.
What's that?
Min and max,
Yeah.
for the majority of them are below like the 3 standard deviations.
Okay, so, well, a couple of them are below 3 standard deviations, right? If we look at what's going on in your minimum values there.
Oh, so my social support is above that 3, and so is my BAS.
Yeah, so I've got some low scores on with MSPSS and the NOS. Like, Bass reward is kind of right there. Okay, so I've got, again, if we're just kind of ballparking stuff, you know, say 3.3 is associated with P less than 0.01. So yeah, some stuff there. Are we concerned by this? What do we think? What do you think, Lindsay?
Maybe a little bit, but not overly concerned.
What's my big save? So we do have some values that are hitting the low end. Nothing too much on the high end. Pretty good there. We do have some low values that are giving us reasonably sized Z scores in terms of absolute value. What's the thing that's saving our bacon in terms of being able to tolerate a lot of stuff?
The max values aren't as extreme.
Okay, max values aren't as extreme. That still doesn't help us if we got like some really big small values. What's
Your sample size?
Yeah, my sample size. So I've got 335 people in this sample. For psychological research, this is pretty big, right? And if I get a sample of that size, am I expecting to get some folks out on the fringes? Probably, right? And if I go through and I take a look at my variables, I mean, I can see, like, so for my MSPSS, I got a couple folks hanging down there at the end who are really, really not feeling supported, right? So those are probably where my really low scores there are coming from. My NOS, I had some down here, like people who were very much not into engaging support networks, right? So that's sort of kind of interesting, right? So is there anything here that looks like sort of individual values that would go through and really start jacking around with my mean values or sort of estimates? Probably not with over 300 people in this sample. Okay, so we're probably going to be okay, but in my screening, would definitely want to go through and maybe sort of identify what for probably the MSPSS, maybe for reward for NOS, just kind of note which, if there's sort of notable values that are kind of falling down there below that. And this is all relative. There's not a hard deadline. I can't say like, oh, if it's above this threshold or below this threshold, certainly always talk about it or not. It all kind of depends. And that's going to be an important concept to recognize as we start to get into some of these regression diagnostics, because you're going to have general benchmarks for what sort of maybe sort of warrants a closer look, but if you actually look at real data, you may have like 20 different values that are all falling down there, and so then like, what do I do? A lot of this is just looking at like relative cases. What are the ones that are kind of like hanging out there separate from the rest that might require some of my attention? So extreme values, not probably, I mean, maybe some things I would note in a screener, but not anything sort of looking too bad. What about looking here at this scatter plot? So this is looking at the bivariate relations of all variables in my model. What are we looking for in these plots? Why did I generate them in the first place? Why do we care?
Follow a linear pattern.
We want to see that our associations are linear, and then what else? Want to be linear and homoscedastic, right? I don't want to see any weird fan shape patterns and things like that, right? I'm assuming, again, my assumption is multivariate normality, or that my bivariate relations are linear and homoscedastic, right? Anything that's looking nonlinear in this matrix. And so when you're looking at these, so this is going to be so for here, it's kind of just the inverse of things, and so having both is maybe a good way to go through and pick things up. So with this, here's MSPSS on the X, AAQ on the X, VAS on the X, and so here's this, right? Anything that looks nonlinear.
One under the BIS total.
Which one?
One under the BIS total.
EIS and NOS, yeah, that one.
This one?
Next, no, down. Yeah.
That one looks nonlinear?
No, well, I guess.
What is it supposed to look like?
It's just like
I don't
scattered
know what
everywhere.
any
Yeah,
of
it's just
these
kind of
are.
scattered, right?
Most of them-
As I was going through and taking a look at this, right, I was like, maybe this one. I don't know, like, do I have something that's is kind of like curving off on this? When we go through these scatter plot matrices are a nice way to pull up and look at everything kind of all at once, so you're just not going through iterations in SPSS or SATA about all possible things. But I was looking at that, I'm like, maybe is there some sort of like curvilinear thing going on here? So if we go through and we take a look and pull this up and actually look at the scatter plot itself, here I've got the green line is just the best linear association there. This red line is a lowest line, and so it's kind of an adaptive, it just kind of fits the shape of this stuff. Up close, are we seeing nonlinearity going on in this? Not really, right? Up here, it looks like maybe it's a little bit suspicious, but, and then also maybe I'm like, boy, do we have problems with heteroscedasticity here as well. Because if I'm just looking at this, I'm seeing there's a decent amount of variability here and not a whole lot there. But if I actually pull it up, I mean, I've got just a couple of values out here, but it's not looking like this is actually too much of an issue, right? So on closer examination, probably feeling okay about this. People seeing why I flagged this when I was looking at it, and then when we actually pull it up and take a look at it, it's not too bad. My line is looking okay. My lowest line gets a little bit of a bend here, but that's just getting pulled down by these. It's not anything that's sort of causing too much of a concern here. All right, so I'm fine with that. Maybe I'm going through and taking a look and like, what's going on right here? I don't think that this is a nonlinear association, but it looks like things get a little sparse up here. Am I having everything converge and I'm not having, do I have a problem with heteroscedasticity here, right? So I pull this up for a closer look, and again, not anything too bad, right? No concerns with linearity, right? And here we're still seeing, if we look, kind of the spread of scores looks pretty good. Like up here, if I'm just focusing on that piece of things, then everything's hanging out above there. But these are, I'm only going to get a few observations here at the top end of that, so I can't give too much attention to that piece of things, right? So I'm not going to sort of hyper focus on there. So again, if I'm looking at sort of about here through here, it's not identical, but I think the general spread of scores is similar. So I'm not too worried about that either. Yeah.
So I feel like I've never been good at just like reading these types of plots anyways.
Yeah.
Is there like a number or like what should we look for is there something that we can look for whether we plot it like with a line, like something we can check or something that will show us if it's actually, cause like to me, that does not look linear, but the line.
I agree.
I'm like, it just doesn't make a lot of sense to me in terms of like, so is it,
Yeah, can you draw a line?
yeah, well, yeah,
No,
like,
cause some of them are like the most difficult, the most easiest one are parabolas, like if you see like.
well,
things like
right,
that,
yeah, I
you
could
know,
figure
just-
that one out,
Yeah.
but like that in terms of,
With this, you got kind of and if I was playing guess the correlation, I would have missed because I would have probably done something that sort of.
well, yeah, that's what I was saying.
The problem is you've got all that stuff down here, and if I draw that line up through here, then I'm not capturing that association right there. If something's nonlinear, you'll probably see it. You'll probably sort of catch it. It'll be fairly apparent, okay? And so what we've done here is I've plotted a sort of a line, and sort of this is the combination with, and I did this in Stata, but you can do the same thing in SPSS. We've got this green line is the best linear representation of this. This lowest line, this is just kind of a flexy thing that we'll go through and do. I'm getting a little kick up here at the end, but that's just because I've got a couple of high values at the end that's pulling that up. There's nothing in here that would suggest to me that this is problematic.
So if the red like squiggly line, for example, is like way off from the limit, like if it's like really
Yeah.
squiggly.
If you think about something that, let's think about an exponential function that's sort of going like this, right?
Right,
My sort of regression line might sort of do something like that, but then I've got a lowest that goes.
Yeah.
You know, that would make me say like, oh, this is potentially problematic, right? But again, that nonlinearity, you're gonna probably see it pretty easily, right? The bigger thing to sort of try and get is heteroskedasticity. A lot of times people will over-identify problems with heteroskedasticity because like, well, right here for these last things that there's almost no variability in these scores relative to all the variability here. Like, well, sure, but that's probably just a function of like only had a couple of observations score that high. And so this isn't actually, I don't have enough observations there to make a strong claim about heteroskedasticity there. Heteroskedasticity too is, we'll get into this, we're looking about something that's about 3 times the spread at the highest point is the lowest point. And that's actually a pretty pronounced sort of difference, right? So again, we want to go through and look for big errors. If there's stuff in there, you'll probably notice it. Now, that's not licensed to just claim everything's fine, right? I want you looking at it carefully, but so it's like calling all of your distributions unremarkable. Don't do that, right? But yeah, if there's something there, you should probably do it. And Haley, as much as you all might hate to hear this, like this is why I have like so many screen problems in this. It's hard unless you just get exposure to data and start to see something that looks really wacky after you've done a bunch of these and seen them. Yeah, I know that happens all the time. That's nothing to be concerned about. It's a lot of just trying to find out. So, Allison, did you have a question?
Not really. I was just gonna say, is it more like thinking, is there a different, like not really thinking like, is it linear, but like, is there something else that describes it
Yeah.
better?
Yeah.
I don't know if that helps.
Yeah. So that's the thing. If I get a big ass cloud of points, it's not a nonlinear relation. I mean, like a line doesn't fit great, but there's nothing else. There's no other shape that would fit that better.
okay.
And so then I don't have to worry about it. So does a line do a great job of describing the relation between these two variables? Ish, kind of, right? But there's not clearly a different shape in there that would sort of better capture sort of the relation between these two things. So yeah, that's a good way to think about it.
I feel like if you start seeing like patterns like that,
Yeah, that's a problem. for
I mean,
sure.
obviously these are.
Here's like-
Oh, yeah.
That's,
Okay, people comfortable with this?
oh, so I can see how you thought okay.
Yeah. Okay, so. When we go through, and so what we're gonna say is we've gone through here and just jumped ahead from a lot of the stuff on our screen, right? We look at plausibility, that's good. We looked at missing this, we didn't, but I did, and it's fine. That's good. Looked at our univariate distributions. We're feeling good about that. We looked at extreme values. We got a couple on there, but nothing that's super concerning. We looked at our bivariate relations to make sure that they're linear and homoscedastic, and they're nothing sort of big coming up there. Okay. Biggest thing we probably see in that sort of note and thinking about going forward is that negative skew on our outcome variable, right? And then some negative skew on maybe another variable, but like overall with this size of data, not anything that's going to ruin my model, but something I want to sort of keep in mind. Basically screening at this level, like we're looking for usual suspects. If the same case or the same variable keeps coming up again and again and again and again, that's our sort of that's our signal that, hey, maybe I need to think a little bit more carefully about what's going on in this case or this variable, so on and so forth. Okay. So now we've gotten into the regression diagnostic piece of things. Okay. And so we're going to go through and say, all right, what I want to do is start by looking at my residual plots. Okay. What I'm going to do here is I'm looking at my residuals. I want to see that my residuals are normally and independently and identically distributed, right? Here, I've got a situation here. What we'll see on when we run this on the x-axis, we've got our predicted values of y are sort of based on our model, right? The outcome that's predicted, and on the x-axis, we've got a residual estimate. Okay, here we're looking pretty good. Residuals are independent, are normal, right? They're kind of all stacked up. You can see kind of them really kind of clustered around sort of this midline, and then they kind of sort of fan out sort of at the end. They're identically distributed, independently distributed. They're all kind of like hanging out there. This is what we like to see. That's good news. Okay. Here in panel B, we've got non-normal residuals, right? If I go through and I sum all of my residuals, they're all equal to 0. Here's the mean. But what I've got is I've got sort of a negative skew to those residuals. Everything's kind of packed up on the center line, and things then are sort of skewing down. Problem here, I risk attenuated standard error with that negative thing. My standard errors are going to be too small. So this would be something I would be concerned about. Am I missing a variable? Is there something in there? Is that just what things look like? This should raise red flags. Here, I've got my residuals are indicating a non-normality in my, or excuse me, a non-linearity in my data somewhere. I've got residuals. You see that, Haley?
Yeah.
That's a upside down U shape. That's something telling me that there's something misspecified in this model, either the relation of my predictions, or I've got variables in there. There's non-linearities that I need to go through and worry about. Okay. And then panel D, here I have something that's heteroscedastic. Okay. At low ends of my predicted Y, things are very, very little variability. As my predicted Y's increase, things start to fan out. Rule of thumb, right, is we're sort of thinking about severe violations as indicated as a spread 3 times at the widest versus the most narrow. If I take this and multiply it 3 times or so, it's still not to where we're at there. If things aren't perfect, things will never be perfect, particularly if you don't have very, very large samples. Things are always going to look funky. What you just want to do is sort of say, like, is there sort of clear deviations there that start to cause concerns? Here again, what we would worry about is worried that we're going to underestimate standard errors, because as we see that pattern out, as my predicted values increase, my errors increase. It's associated with attenuation of standard errors. So these are things that start to help us contextualize the stuff that we're finding in our model. Okay. All right. So if I go through and I take a look at, and don't worry about how I got these. Next week, we'll go through and talk about how you go through and get these. But here I've got my predicted values, my standardized predicted values on my x-axis, and my residuals on my y. Okay. What I'm wanting to look at here is just focusing on normality and distribution of my residuals. Are my residuals looking? Do I have any evidence of non-normal residuals here? No. I mean, here's my 0 line, and the mean of my residuals will always be 0 because they have to be, right? I included the lowest line on here. It's got a little bit of a bend, but it's not really anything looking non-normal with these residuals. What's the thing that's weird about these residuals? What's that, Haley?
They're all clustered, they're like pretty close together. Like
Where are
towards
they
the,
pretty close together?
like the, towards here, like towards the 0.
Along
Like
here?
along, yeah.
Okay. Yeah, and we kind of hope that they're kind of clustered around that, because that's sort of telling us about normality of the distribution. And we've got some lower stuff down here. That I'm like, oh boy, is that non-normal? We'll go through and take a look. Johnny, what's?
I feel like it has a little bit of like a funnel shape.
Yeah, we've got kind of this edge kind of right along here, right? Where we've got a weird thing where I've got it's not that nice cloud shape that we saw in other pictures. I've got kind of a hard edge kind of running along that line, right? And I'm like, what's that about, right? Well, remember, if we go back through, oops. Remember this, right, our outcome? Everything's stacked up, we got a negative skew, and everybody, like the most people here are reporting high levels of social support, right? So if I go back to my prediction model and I go through, and remember that if we're going through taking a look, here I've got a case, this is an under prediction. My residuals are calculated my observed score minus the predicted score. So this case right here, I've under predicted the value, right? This person scored much higher on social support than what the model predicted they should provide. And so I've got a large positive residual. It's kind of the opposite of what we would think, but we've got an under prediction here. Models expected this person not to report the level of social support that they had. Here, we've got an over prediction, right? The model says, oh, hey, you should have sort of high levels of support, and this person didn't. So now we've got this, so we've got an over prediction of sort of what was going on there, right? And again, this is all just calculated as the observed value minus the expected value, right? But when we see this edge right here, right, what we've got is essentially, if I've got a whole bunch of people reporting max values of social support, and so here I'm under predicting that because they reported max values, but my model said they shouldn't. But as my expected value of social support increases, and we get closer to all those people who actually had high levels of social support, we just get a hard edge sort of going on right here. So what we've got is basically, because we've got in our predictor variable, because we've got a ceiling effect and kind of like that negative skew, what it's doing is it's giving us a unique feature in this residual that's not the nice cloud that we would see, right? And so it's not necessarily going to be problematic, but it just makes our graph look a little bit weird, right? So think about it this way. If I've got, like, say, 30% of my sample reporting max levels of social support, and these are all those people, here I'm under predicting, but my under prediction gets better and better and better and better until I get to this point, and then we tip over and we've got people. So we've over predicted again, but that's what's causing that piece. So again, sort of thinking about if you're seeing weird features in your data, go through and investigate it. Like, what's going on with this? This seems not a random thing. So how do I go through and understand it? Okay. But in terms of non-normality and homoscedasticity, do we have sort of big concerns with what's going on here? Probably not. Okay. Here, same thing, just sort of producing this in Stata, looks a little bit different. But essentially the same thing. Here's my lowest, here's I've seen that hard edge right there. So, yeah.
Would I describe this as a hard edge, like it's miscreating, like?
I mean, that's not a formal term. I'm just putting words to what I'm seeing in these data, right?
I just never know what to say.
Yeah,
Like, it's kind of weird.
That's all right. Just kind of weird is fine, so long as you tell me what it's kind of weird, right? So got a straight edge on this stuff. And yeah, this is a weird thing. This is not a great example of what, like, we would sort of a stereotypical case where it's a true, but again, this is what happens psychologically, because you can only have on my arbitrary scale, your level of social support can only be so high. And so we've got kind of a hard stop on that versus if this was something like income or like something like that other fields use where you kind of go through and have sort of more levels, then you can go up there, right? Yeah.
Similar to that concept of the floor.
Yep, so floors and ceilings and stuff like that.
Ceiling.
We'll start, yeah, we kind of got a ceiling on this. Because I don't know, if people on who I sampled could report higher levels of social support, they probably would. And then you can think about this, and just kind of exploding up and filling this space is probably what would have happened. But I just have an arbitrary truncation on how much social support they can provide. So, you know, this is trauma exposed undergraduates. But they're still sort of folks who are here in college and sort of generally do okay for the most part. So feeling pretty good about stuff. Now, if I were to get a different sample, different population, this might look very different. But for who I've captured, this is kind of what's happening. All right. So my residual plots here, I'm looking for linearity and also looking for homoscedasticity. But we can also go through and produce a couple of different plots. Okay, our probability plots are histograms. Our normal probability plots. So this is just taking this and sort of testing normality. Specifically, what we do is this is just capitalizing on our abilities as humans to identify edges and lines pretty well. Okay, and so what we would do here with histograms, you already know about, but with these probability plots, what we're seeing is under normal circumstances, everything will fall on this sort of 45 line. As we start to get violations of normality, things that are positively or negatively skewed, or kurtotic, what we'll see is starting to have deviations from that sort of diagonal that are pretty easy to see and detect just because we're pretty good at that. So a couple of different plots. The PP plot, this is the distribution looking at the cumulative distribution of the observed data, of the cumulative distribution of the target function. Quantile plot, your QQ plot is a little bit, I mean, they're functionally the same. They just kind of calculate them a little bit differently, but they're interpreted the same way. If we look at this graphic here, we'll see your normal data, follow a nice plot. If you got something with kind of a rectangular distribution, that negative kurtosis, you get kind of this S shape going on. Positive kurtosis, you get an opposite S shape, so a curve, kind of what is the cubic function. So you get two, yeah. So it kind of goes like that, right? Here, a skewed distribution. So basically across all of these, you're seeing different shapes, right, relative to just that line. And Johnny, and some of the stats stuff that you took with like a lot of focus on some of these probability plots, and sort of like using that to determine normality of data. Yeah. Okay. So we don't see these as much in behavioral sciences, but if you're in other areas of statistics, this is something. So happy to do sort of reuse some of these in some previous stuff. Yeah. So if we go through and we take a look at our data, right? And this is, again, we're plotting out the residuals. Here on, this is your PP plot here. You'll see here's the diagonal. We're getting a little bit of deviation off of this, but it's not too bad. I mean, things are looking okay. Here, if I go through and I get a histogram and superimpose a normal distribution on it, again, it's not too terrible. We've got, it's fine, but it's not bad, right? And again, just think about this as different ways of evaluating the normality of your stuff. Honestly, if I were to look at this, I might start to worry about like seeing all this stuff down here. I might be like, oh boy, do we have some problems with the negative distribution or negative skew in our residuals? Here it looks like it's probably not too bad. Okay, now this is your overall distribution. So now if you start to see sort of big negative skew here and something different, I mean, it's you're not out of the woods, but it's looking like it's not terrible. Yeah, Johnny.
I just had a quick question.
Yeah.
So, in one of my other stats classes, they just taught us that in like the part of the residuals, if it's like the $1 rule, that if you can put like $1 on the other side of the line and it balances things out, it's probably okay. Is
Okay,
that
that's,
something-
no, I had not heard of that, but that's a good way to think about things. Yeah, if I could go through and drop an observation here, and that makes that sort of look better, then you're probably gonna be okay. Yeah, that's a nice way to look at it, yeah. And so basically, it's this balance of like wanting to catch things, but not over-identify stuff is problematic. Yeah. So again, same thing, this is just instead of a different look here. Okay. All right, so what we've done is, and think about like working through our checklist, right? So it's gone through and our residuals look normal. They look relatively homoscedastic. And it does not look like there's non-linearities in our residuals. So we're going through and starting checking through things and feeling pretty good about stuff, okay? What we want to do now is start looking at problematic cases, okay? These are gonna be some of those, think about these as extreme values, outliers. Stuff that can start to throw off our estimates. And so here, when we're looking at this in univariate space, it's easy. We can just say high Z value, low Z value, something along those lines. When we start combining variables together, we have to get a little bit more nuanced. Some different sort of terms we'll go through trying to describe what's going on here. First is a discrepancy value. A discrepancy value is defined by a difference or discrepancy between my observed and my expected value of Y. Okay, this is just an evaluation of my residuals. Discrepancy refers to Y space. Okay, here's what I observed. Here's what my model predicted. Am I way off base with that? Right. So if I've got a handful of cases where I've got a really, really large discrepancy, I thought this person was going to score really, really high and they scored really, really low. And I got this massive residual, then maybe I might be worried about that if I've got a lot of those, maybe. Okay, so we're going to take a look at our discrepancies, looking at these in terms of our residuals. We're also going to talk about leverages. Okay, these are going to be caused by pilot leverage values are going to be unusual value variables in or unusual values among our explanatory variables. Discrepancies, this is Y space. Leverage, this is X space. Okay, and what we're going to do is we're going to look at leverages. Think about these in multivariate outliers, right? These are weird combinations of our predictors, okay? And then last, we've got influence, okay? Influence refers to the extent which inclusion, exclusion of a case is going to impact my model or individual coefficients. My influences, these are a combination of my discrepancies and my leverage, right? So we've got stuff in X space, stuff in Y space, and then essentially the function of the two put together. So if we go through and take, I really like these panels because this can start to, you can start to see how different combinations can start to do different things. Okay, so in this first panel, what we have here, we say here these 4 points, that's our regular sample, and then this black dot is the one that we're sort of taking a look at here. Here we've got a case that's a moderate discrepancy, right? The discrepancy is our residual. Expected value of Y is right here. Here's what we actually observed. It's not a huge residual, but it's a modest discrepancy value here, right? But low leverage, okay? So again, remember that leverage is a weird case in X space. In X space, I don't know, here's my low value, here's my high value, kind of falls within that space. Like this is not a strange value for my X, right? So low leverage, not worried about that, not weird in X space, right? And low influence. If I go through and I take a look at the solid line, that's my actual estimated regression line. And the dashed line is the estimated line if that case were not to exist. If I pull that out, I see a deviation in my intercept a little bit because it kind of pulls it down. But overall, low influence on this, right? The inclusion or exclusion of that at this point actually doesn't change things too much. So really, this is, I've got a high residual here, but like it's not actually impacting my model a whole lot. Contrast this with the second panel here, right? Here, we've got a large discrepancy. Again, if I look at sort of, if this value is not in the model, here's my expected value. Here's what it actually is. I've got a pretty big discrepancy here. I got what would be a large residual. Okay. Now is my actual residual on this in this estimation do I actually have a large residual in this? No, I don't, right? Because with this point in the data set, my prediction line is actually about perfect, right? The problem is this is screwing with my whole regression model and it's bringing everything down so that it can account for that, right? So this is what we'll start to see. We'll talk about using studentized deleted residuals. Because what I can have, if I just have this in the model, my residual value isn't very large for this, right? But if I estimate a model without that value in and look at the discrepancy, now I've got a pretty noticeable thing going on. So what we can see is some of these problematic values can mask problems, right? And so we want to be careful in terms of how we're going through and looking. So just my raw residual is close to 0, but what we'll see is my studentized residual, my studentized deleted residual is actually going to show me that this case is actually exerting a huge influence on the estimation of my regression line. So
Studentized,
what's up?
what did you call it?
Studentized deleted residuals. We'll get there in a couple slides. Lots of different types of residuals and sort of different formulations and things along those lines, but we'll get to that in a moment. We also see a large leverage value here. Here's the rest of my X values. This is a weird X value. It's way out there, right? So I would say I have a large leverage value and then high influence. The difference between the regression line with this case in the model and without the model is huge, right? So in this situation, we've got a point that is associated with a large discrepancy, a large leverage, large influence. This model looks very different with this one person in versus this person not in. Last panel here, a little bit different. Again, low discrepancy, right? Whether or not this case is in or is not in the model, our residual is still very, very low. So I'm not concerned about that. What I do is I have a large influence, or excuse me, a large leverage in X space. This is a weird, in predictor space, this is a weird case. It's way out there. Now, I don't have much influence on here because the regression line is functionally identical with that case in it without. The problem is what will happen with that? It's going to shrink my standard error, right? Just looking at this line, so I mean, this is kind of a manufacturing thing, but the line looks pretty good. But if I go through and drop a point way the hell out there on where that regression line would fall normally, it makes that model look a whole lot better than if I were to pull this out. If I pull this out, there's a lot less uncertainty. Basically, I'm dropping an anchor right onto where this line would go. And it probably makes that model look a lot stronger than it should be if I pull that case out, right? So here, low discrepancy, low influence, but a large leverage, it's going to start to impact my standard errors. So again, I would need to question whether or not I want to have that. Yeah.
So do you need to have large discrepancy and large leverage in order to have high influence?
Generally, that's what'll happen. It's kind of a product of the two things, but sort of not always. There's sort of different things that can go in. Again, when we get into multivariate space, things start to get tricky. Okay. So diagnostics are discrepancies. Usually what we go through, again, discrepancy, this is just our residual value. Residual values, we talked about residual, getting comfortable with those. Traditionally looking at standardized residuals, raw residuals is just the raw difference between my predicted value and my outcome. It can kind of be hard just looking at your raw residual to determine whether or not it's a big deal or not. But if we go through and we standardize those residuals, that puts it on like a Z-score metric. Now we can start to identify if I've got a standardized residual of 4, is that big, Allison? On a Z metric? Yeah, that's pretty big, right? If I have a raw residual of 28, is that a big value? Who knows, right? And so we'll go through and look at our standardized residuals to go through and take a look at this. Now, there's lots of different options in terms of what types of, how you go through and standardize. The one I'm going to encourage you to use is what's known as an externally studentized residual. Okay. In SPSS, we talk, this is labeled as a studentized deleted residual. In Stata, it's a studentized jackknifed residual, right? What people call these is a little bit different, which makes it a pain in the ass to figure out what the hell's going on with stuff. But essentially with this studentized deleted residual, or this externally studentized residual, how it's calculated is the difference between the observed value of Y for whatever case we're looking at and the expected value of Y in a model that excludes that case. Okay, so if this case isn't in the model and we go through and estimate my regression line and then use that model to say, hey, for this case, this is what the value should be, this is what the actual value is. If we see a big difference in that, that's gonna lead to a large studentized residual. And this is exactly sort of the situation that helps address this thing here. Because if I just standardize that residual, it looks like I'm doing pretty good, right? But if I use my externally studentized residual, I can see that this is actually problematic, okay? So this is why we go through and use this. Now, if we've got, if the observed outcome for my case is consistent with sort of expectations in the larger set, then I'm gonna have the absolute value of that is gonna be pretty low. If my model, if this individual case is pretty in line with what we would expect in general, gonna have a low studentized residual, we're good to go. But if my observed outcome deviates from expectation in a model that sort of just doesn't include that, basically I'm gonna get a large value. It's gonna say the model that I would estimate without this case in there is very different than the model I would estimate with this case in. That's signaling to us that we've got a problem with this value or with this observation. Okay. Our residual or studentized residual here follows a t-distribution with n minus p minus 2 degrees of freedom. P is my number of predictors. Okay. Really want to go through plot the distribution of this, not just look at my individual values. Want to go through plot, see what they're looking like, right? But again, sort of benchmarks for a large studentized residual somewhere between values of 2 and 4. Again, it's the same thing as score. Like you just, again, as my sample starts to get really, really large, I'm going to have weird cases in there. That doesn't necessarily mean they're problematic. It just means I got a big case, but they're a big sample size. Just wanting, but these are just kind of general benchmarks. This is why with all these things, plotting things out is super, super helpful, because a lot of this comes into like what's relatively problematic relative to other stuff. Yeah.
You said P stands for the number of predictors.
Number of predictors. Yeah. So the number of people in my sample minus the number of predictors in -2, that technically defines the distribution of these studentized residuals. So it's not really a Z distribution, it's a T with that many degrees of freedom. But again, if you've got a reasonably large sample, they're gonna be pretty close. So if I go through and I take my studentized residuals from my model and I go through and I plot these out, looking at a box plot, looking at a histogram, looking at my descriptives, right? Am I seeing problems in terms of sort of my raw values here?
Yeah, well, kind of, I guess.
What's that?
Some stuff on the,
Yeah.
I don't know, left.
Yeah, on the down, like what's my minimum value for my studentized residual?
Oh, it's pretty high.
It's -4.3, right? So it's large, and so definitely something I would flag and be like, hey, what's going on? If I look at my box plot, I can see it's case 291 down here. There's some other stuff kind of trailing off. If I look at my histogram, I've got some folks down here that are kind of separate from the distribution. These are all cases I might want to like take a look at and just kind of, again, we're not going to make any decision based on any one individual score. What we're looking at is accumulation of evidence. Do I have the same case keep popping up again and again and again and again? Those are the ones we're going to focus most of our attention. So again, if I go through and I take a 291 has a studentized deleted residual of -4.3, -3.7, -3.5, that kind of gets at sort of these group down here. This one, I guess I didn't flag. It's just kind of saying, hey, these are kind of the cases that are on, I got my eye on you. So keeping an eye at what's happening with this. Okay. So again, here we're seeing a negative residual that's saying that the observed value of my MSPSS is, yeah, we're overestimating my outcome, right? It's Y versus, yeah. Yeah, so my observed value is less than what my model says it should be. These are people who are reporting lower levels of social support than what my model says they are, and to a pretty big extent. Okay, so based on information from all of my predictors say this person should be feeling pretty supported. When I actually look at it, they're not. That's what's going on with this stuff. Same thing here, just sort of looking at SATA. Colors are different. It's not too bad. Okay. All right. Talking about leverages. Generally, we're looking at our leverage values through leverages or hat values. What we're doing here is, again, thinking about working in X space. If I just the assessment of my leverages has nothing to do with my Y. I don't care about what's going on with Y. Just looking at my X. We're just looking at X space here. Okay. And again, my leverage is going to be an index of the distance of my in multivariate space of this person with the centroid of the predictors after accounting for the correlated structure, right? So again, remember that your centroid is the sort of average mean, and so the mean value of all your predictors out in, we can think about it in 2-dimensional space and 3-dimensional space. When we get to 4-dimensional space, then sort of I kind of lose stuff, right? But in 3-dimensional space, it's kind of hanging out like right here is the middle of everything else, and then I've got a value that's hanging out here. That distance is determined is sort of what my leverage is based on, okay? Now, leverages, standard leverages are going to range from 1 over the number of people in your sample to 1 with a mean equal to the number of predictors plus 1 over n. Okay, so this is telling you the range of what your leverage values can be, what the average leverage value in your data set will be. Okay, now SPSS runs a little bit different. They calculate a centered leverage. You don't have to worry about it so much. Just know that you're running a centered leverage and not a raw leverage. Here, your values are going to range from 0 to 1 minus 1 divided by the number of people in your sample. So it's just going to shift things around. SPSS users, make sure you know this. Johnny, if you're using SATA, make sure you know this, and just so because your metrics and your benchmarks will change a little bit. Okay. Now, if I've got a leverage that's greater than 2 times the number of your predictors plus 1 over n, kind of a minimum threshold for further exploration. Again, looking at anything greater than 3 times p plus 1 over n. Basically, what we're doing is we're saying 2 or 3 times the mean of your leverage. Same thing for centered leverages, something that's 2 to 3 times the mean. This is kind of your minimum benchmark for what you might want to go through and look at a little bit further. Now, know that this is a minimum threshold. This is a very, very, very liberal threshold for what I'm going to flag as potentially problematic. When you actually run your data, you're probably going to get a whole lot of cases that are above this, right? So again, this is where it starts to become important that you're thinking about, okay, who are the heavy hitters in here? Like, what are the big ones that I need to be focusing on, as opposed to sort of chasing down because if you go through and just start kicking everybody out that exceeds 2 or 3 times your average leverage, you're going to start to lose a whole lot of people, right? And you're going to start to exclude people you don't need to exclude people. Okay. So just be aware of this. Okay. So again, in SPSS, I've gone through calculated leverage values. These are my centered leverages. It's kind of my box plot. This is sort of the distribution here, right? And so we're seeing skewed distribution, but you kind of expect that. You expect most people kind of hang out here, and then there's some bigger values, right? If I go through and I sort of go through and test, I've got a total of 9 cases with the centered leverage that exceed 0.036. This is 3 times your average value. So P, number of predictors, we got 4 predictors, right? Divided by 335 gives us 0.036. This kind of gives me my cut point for what my, 3 times the mean value of this. And so if I go through, I've got 9 cases that are falling with centered leverages above that threshold, okay? And so we've got kind of the folks that are out here. This one is probably kind of the one that I'm sort of going to flag and sort of be most problematic, but then we've got kind of maybe some clusters down here that are maybe worth noting. Same thing in SATA here, it's a little bit different. What we're doing is looking at just leverages as opposed to centered leverages. So our expected value changes a little bit different. What's cool And we'll talk about this with, remember that leverages are essentially, these are our multivariate outliers. And we're never just identifying multivariate outliers as, oh, that's a multivariate outlier. Always want to identify like why, what combination of scores is making this a multivariate outlier. We'll talk about how to go through and do that in SPSS. Statistically, we kind of hijack some regression to go through and determine how, so what variables are contributing to this being a weird case. One thing that's pretty easy to do in Stata that I kind of set up is if I go through and use this extremes command. And so I'm wanting to tell it to give me extreme values for leverages. And so it's going to be the top 5, and then give me my participant number, MSPSS, AQ, BIS, or BAS, BIS, NOS. And so to give me the top high values, right? And so what I'm seeing here is if I go through, here's my highest leverage value, and then my next 4 highest. Here's my participant number, and then here's the actual values that I'm seeing for these cases, okay? And if I go through, what I'm seeing is a total of 5 cases here with leverage values exceeding 3 times the average, which is, we got more of them with our centered leverages. If we're just looking at regular leverages, we only have 5 cases. But if I go through and I paste up just sort of my descriptives for all of these variables, what I can start to see is start to identify what things are, why is this a weird case, right? So here, if I look at my largest value, which is 276, I've got an MSPSS value of this person of 6.3. And if I look at MSPSS 6.3, so this person has a high social support value, but is it weird? Not really. It's about what I would expect. My AAQ, my psychological flexibility, this person has a value of 16. AAQ, the mean is 21. Okay, so it's a little bit low. BAS reward is 11. All right, now that's real low. So I've got low reward sensitivity relative to the mean. This behavioral inhibition is 12. And now that's also really low there. And my NOS is 66, which is really high. So I've got someone in my set who's reporting high levels of social support, but lower levels of psychological flexibility, which is a good thing. Low levels of reward sensitivity combined with low levels of behavioral inhibition, which is kind of weird. And it was really not into sort of utilizing social support, but still reporting lots of social support. And so we've got a weird configuration that's making this person be weird in predictor space, right? And so what we can start to do is go through and say, hey, in terms of my predictors, like where is this person at, right? And what we've got is someone who's low in places we wouldn't necessarily expect them to be low, and higher in places where we wouldn't expect them to be high, because we've got correlated variables. If I've got someone who's very, very averse to utilizing support resources, I would expect maybe that psychological flexibility score to be lower. And so maybe a higher levels of my behavioral inhibition. So it's just a weird combination that's getting flagged here. And so again, sort of make a note, we can't just identify, say, oh, these are cases that are weird in X space and sort of have high leverages. What we need to go through to do is then explain sort of what's going on. Why is that person strange? Because again, that's going to tell us, is this someone who should be in our set? Is this person providing valid responses? And like what subpopulations of the community have I not captured, right? So a lot of diagnostic detective work going on with this stuff. All right, we'll stop there. We'll jump back in with and finish this stuff up. We're getting close. We'll go through, finish this, work through an example next time, and then the stuff on variations on regression go pretty quick because that's not super complicated. Okay. This is the involved stuff. All right. Stop this.